Okay, let's take a look at a transformer problem here. So I've got some kind of AC voltage source over here on the left side that's going through a resistor, which is modeling the resistance of our power lines. So we call that R line. Then it's being used in a transformer. That transformer is transferring the power over to this other circuit here, which is then being used in our home. First thing we want to know is what the efficiency of this system is. Then we want to figure out what the voltage at the source is. And then finally we want to know what benefit we would get if we changed this resistance in the power lines from 10 ohms to 5 ohms. So the first thing I'm going to do is figure out this efficiency piece. So I know that my efficiency equals my power out over my power in, and that also can be written as P useful over P produced. So in this case, my useful power is what's being used at the house here, this 200 kilowatts. The power being used by my home is useful to me. This power that's being used over here in the line, that is not useful power to us. That's being wasted. So it's kind of a necessary evil in order to get this power from our power plant to the house. We're going to lose a little bit in these power lines here, but that's not useful to us. It's representing our losses. So P useful, we said we know that already. That's P home. So I can fill that in now. And now I need to figure out P produced. Well, I know due to the conservation of energy that the amount of power I'm using in the home and in the lines has to equal the amount of power I'm producing. We can't just have power disappearing in nowhere and being produced out of nowhere. So all the power that's being produced has to equal all the power that's being used. So for my total power produced, I know it's going to be 200 kilowatts plus the power in the line. So I'm saying that my power being produced has to equal the power that's being used. And it's being used right here in the home and here in the power line. So now all I need to do is solve for P line, and then I will be able to figure out my overall efficiency. Okay, so if I take a look over here right now, I don't know the current on this side, and I don't know any of the voltages, so I really don't have enough right now to figure out the power in the line. Let's think about how I could figure that out. So I know my equation P equals IV. So one way I could do it is I could figure out the current over here, and I could figure out the voltage across this resistor, and I could use that in P equals IV to find the power. But we know we have a couple other forms of this equation. So one, P equals I squared R, and then we also have P equals V squared over R. So think about how we can find these things. Well, I know I can find my current over here using P equals IV. And I know that my voltage here has to be 120 volts, because if we drew a KVL loop right here, we would have V2 equals 120 volts. So, see, I know V2, I could use the A value and get V1, but that doesn't tell me the voltage across the resistor, and I don't have the voltage here at the source, so I don't really have an easy way to find the voltage there. Let's take a look at the other way. Let's look at the current. So if I come over here, I say P equals IV, so 200 kilowatts equals my current times 120 volts. Just switch to the calculator real quick. So we'll do 200,000 divided by 120. So that gives us 1.67 kiloamps. Quite a bit of current. So I equals 1.67 kiloamps. Now that I know that current, that's the current going through this whole circuit, now I can use my turns ratio. So I've got A equals the turns on the left side to the turns on the right, which also equals the voltage on the left to the voltage on the right, which also equals the current on the right to the current on the left. And this last form is what I want to use. So I've got 50 equals 1.67 kiloamps divided by I1. Switch over to our calculator again. And I'll divide this by 50. So I get 33.3 amps. So that is my current right here. That's my I1. Now that I have that current, and I know this resistance, I can use this form of the power law, so I squared R, to find my power. So P line equals 33.3 squared times 10 ohms. So we will square this and multiply by 10, and looks like 11.1 kilowatts. So now I can come back and plug that in here, 11.1 kilowatts, and I get an efficiency of 200 kilowatts divided by 211.1 kilowatts. And that gives me 94.7%. So that would be the efficiency of this system. With a 10 ohm resistor. Now what would happen if I change the resistance over here? Well, my power is given, my voltage is given, so I know my current's here. That means I know my current over here. Only thing that's going to change here is my resistance, now going to be 5 ohms. So over here, my power in the line is going to be reduced in half. So I get 5.55. Now I can come back up to this equation and rewrite it to 200 kilowatts over 205.55. See what that gives me. And I get 97.3%. So obviously, as we'd expect, if we decrease our resistance here, we're losing less power in the line, and our overall system becomes more efficient. Now, let's see. So we've answered the first question and the third question. Now, one more question we have is, what is the voltage at the source? So for this, let's go back to using 10 ohms again. So we know V2, that is 120 because of this KVL loop right here. This voltage has to equal this drop over here. So that's 120. We can find this voltage over here using this A value, so A equals V1 over V2. We'll go ahead and solve for that. Let me clear a few of these things off. Okay, so I can say 50, my A value right here, equals V1, which I don't know, that's what I'm solving for, over V2, which is 120. Okay, so then all I have to do is multiply over. Should get V1 equals 6,000 volts, so 6 kilovolts. Oops. Not watts, that was volts. Okay, so now I know the voltage over here. Right now I don't know this voltage over here, but I did solve for the current earlier, and I had 33.3 amps. So that was my current over here. I can use that current with this resistance to get a voltage. So this is just going to be V equals IR. I is 33.3 and R is 10, so I'm going to get 333 volts. Now all I have to do is add these together, because if I drew a KVL loop right here, I'd have my voltage at my source minus 333 volts minus 6 kilovolts equals 0. So my source has to equal 6K plus 333. So I know that the voltage at the source will have to be 6,333 volts, or 6.333 kilovolts. Alright, so now I've answered all three of these questions. I found the efficiency, we just found the voltage at the source, and we already talked about what would happen if I replace this 10 ohm resistor with the 5 ohm. It increases my efficiency.